Let us start this lecture with a thought process. Life is a marathon, not a race. So, if you recall that in the last lecture we basically derived a relationship known as Rankine-Hugonet for a one dimensional combustion well, which covers both the deflagration and detonation, and we also discussed various regimes of the Rankine-Hugonet curve, and in which we pointed out that this weak deflagration and weak detonation are possible, whereas the strong detonation or strong deflagrations are not possible in nature. Therefore, we will be basically restricting our discussion to the weak detonation and deflagration. In this course, we will be not discussing about the detonation as such. Rather we will be talking about deflagration. Before venturing into the deflagration, I would like to take an example on this detonation. That is, basically we will have to determine the pressure of a gaseous stoichiometric hydrogen oxygen stoichiometric mixture at initial pressure of P1 1 bar and temperature T1 you can say 300 Kelvin with a density of 0.8 kg per meter cube. And assuming the product to be gaseous hydrogen only, right? When the fluid density, when the final density of mixture is 3.2 kg per meter cube, and you can take gamma as 1.2. So, basically we will have to look at the pressure of the mixture, this detonation, this would be detonation pressure, right. That means it is basically the P2, and in this we need to basically find P2, and what are the things are given? Given is P1 is given 1 bar, and rho 1 is given 0.8 kg per meter cube, and rho 2 is given 3.2 kg per meter cube. If you look at, we will be using basically Rankine-Hugonet relationship by using we can have Q is equal to gamma minus 1 P2 by rho 2 minus P1 rho 1 half P2 minus P1 1 by rho 1 plus 1 by rho 2. This is the relationship what we had derived earlier. Now, if you look at what is given, like P1 is given, the rho 1 like this is given, rho 1, rho 2 is given, gamma is given, right. These are values are given, gamma is 1.2, Now, you do not know the P2, you do not know the Q, right. Q is basically how much of heat being released. However, it is given the stoichiometric mixture. That means what? That means like 2 hydrogen is reacting with O2 going to water, right. So, I need to find out basically Q. Q is Yi H F I naught, which is equal to Y H2 HF H2 naught plus Y oxygen HF O2 naught minus Y water HF water, right. So, that means I need to evaluate the mass fraction of hydrogen, mass fraction of oxygen and mass fraction of water, and which is from this, if I say this is equation 1, this is equation 2, I can find out the mass fraction of the hydrogen Y of hydrogen, what it would be? It would be basically 2 into 2, right, the molecular weight of hydrogen divided by 4 plus 32, right. 2 moles of hydrogen and 1 mole of oxygen, right. This reaction given in equation 2 are balanced. So, therefore, what it would be? It will be 0.111, right. What will be then oxygen? This is on the reactant side, right. What will be oxygen then? This will be 1 minus that, 1 minus YS2, that will give me 0.889, isn't it? And what will be the product side? For product, the mass fraction of water will be 1, only water is there. So, you can find it out, and then if I substitute these values, and you will have to also get this heat of formation for hydrogen, oxygen and water from the thermodynamic table or thermochemical table, right. And the hydrogen at the standard state, it will be 0, right. This will be 0 and this will be also 0, oxygen, and whereas the HF, where HF water happens to be something 13434 kilojoule per kg, right, because you get mole basically in mole and then divide by the molecular weight, you will get basically in terms of kg. If I put this thing here, this will be 13434 kilojoule per kg, right. Then what you do, you basically substitute these values in equation 1. So, substituting the values of Q and gamma and P1, rho 1, rho 2 in equation 1, we can get basically P2. I can write down this expression in terms of P2, P2 gamma, gamma minus 1, rho 2 minus half 1 by rho 2 plus rho 1, right. I am just using this expression 1 and is equal to Q minus P1 half 1 by rho 1 plus rho 2 minus gamma, gamma minus 1 rho 1. So, I will just substitute these values what I can get, that is P 2 into this is 1.2 divided by 0.2 into 3.2, rho 2 is 3.2 minus 1 by 2 1 by rho 2 3.2 plus 1 by rho 1 0.8 is equal to Q. Q is 13434 kilojoule per kg minus P 1 is 1 bar. 1 bar means you can say it is basically 100 Pascal, 100 kilo Pascals, right, 100 kilopascal. So, half 1 by rho 1 is 0.8 plus 1 by 3.2 minus 1.2 divided by 0.2 into rho 1 into 0.8. So, if you calculate, you will find that P 2 is 13793 kilopascal is equal to 13.793 megapascal. So, which is a very high value as compared to the P 1. We had seen that in a table I had shown you that what will be the pressure ratio, right. Pressure ratio will be very high. In this case it is much higher, like P 2 by P 1. Of course, these are very ideal case what we are considering, but in real situation it will be order of something 20, 30 kind of things, like kind of P 2 by P 1. So, in this case it is happens to be something 130, right, times kind of. So, what we will do now, we will be basically now looking at the deflagration side, particularly the premix plane. So, we will be considering laminar premix plane because it is very simple to handle, that is one thing, and also it is being used particularly for domestic burners where the or in a other application where you do not need to have a very high heat release rate. So, therefore, we will be using it, and it is quite fundamental to the even handling the turbulent premix plane. And let us look at like this premix plane, which was basically invented by Robert Bunsen in 1855, and he developed a basically Bunsen burner. And Bunsen burner, if you see that the fuel is entering into this zone here, and there is of course a stopcock, you can say it can on and off valve, right, that it will be making it off and on for the safety purposes, and there is a what you call primary air port here, and there is a tube which is, you call it as a mixing tube, and once you let the fuel to flow through this, and it will be mixing with the air which will be entering into this mixing chamber through the primary air port, and then you ignite, you will get a flame. Of course, it will be having some dark zone and then luminous zone. But question arises, why the air from the atmosphere will be entering into the mixing tube, right? Because unless the fuel and oxidizer are mixed, you cannot get a premix flame. For example, if I close this air port by this controlling ring, you might have used a Bunsen burner, you can change like that thing, and controlling ring, you can close the air, then what you will get? You will get basically a yellow flame, which is nothing but a diffusion flame, right. So, let us see what is happening in this simple device which is help in mixing the fuel into air. When the fuel is entered into this pipe through the tube, it will be creating a jet. Jet means there is a small orifice will be there through which you will be pushing the fuel in this case at a higher pressure, right, and as a result it will be moving the fluid at a very high velocity, right. So, the fuel orifice will be there, and if I consider this as a tube, right, let us say this is a tube, and this is closed, and then what happened, like there will be a jet, this is the fuel which will be entering, and this is having a the jet will be there. So, as a result what will happen, there will be a jet which will be having, this is known as basically the potential core, and this jet will be having here. Now, of course, this will be having a hole, these are air will be entering into this air, and this is air holes, right, and this is fuel which is entering is fuel, and this is fuel jet. Now, when it is entering this, what will happen, as it is having a potential core. So, this portion is known as basically potential core. What is the meaning of that? Meaning that whatever the velocity is coming from the orifice, right, it will be remaining same, it will be not affected by the air entrainment. Why the air will be entering? Because this will be having a large momentum, and it will be trying to drag the fluid which will be nearby, right. If the air is around, because there is a hole and the air will be there, so that will be dragging the fluid along with it. Like in a similar way, leader in a society always drag the people along with his ideas. In similar manner, the fuel jet in the case of Bunsen burner will be dragging the air along with due to its higher momentum. As a result, the fuel air will be getting mixed, and these are the holes. If you look at, these are airports, these are the airports. Of course, there will be some airports here through which air will be moving once it mix, and this is your mixing tube, right. Of course, you will get a flame. So, holes in the mixing tube entrain the surrounding air, and the fuel air mixed thoroughly in this mixing tube, because as it moves it will be having some momentum, it will be mixing well, and it is given enough residence time for the fuel air to be get properly mixed at the exit of this outlet of this Bunsen burner. And once you of course ignite the mixtures, then the flame will be established. Keep in mind that similar mixing setup or mixing process occurs in case of your LPG burner. Did you see that? There will be some holes, the jet will be there, and this jet diameter, orifice and also pressure will be basically affecting the mixing process, right. So, what are the factors that govern the flame shape is basically the velocity profile at the exit of the Bunsen burner, right. It can be one dimensional profile, right. It can be parabolic profile. Generally, whenever you use a tube, it will be parabolic profile. And under what condition I can get a parabolic profile? Provided the flow is fully developed, right. But however, in this case you will be getting a semi parabolic profile. Generally the tube is given such that it will be getting a, and also as the flame is nearby the tube, then there will be some heat losses, right, from this thing, because the flame will be anchoring, and heat loss to the burner rim. This is known as burner rim, right. It will be having some finite thickness. It is given as a line, but there will be some thickness. So, how to get a parabolic profile? I have already told you, that is by providing sufficient tube length. It is too huge, like particularly for laminar kind of flow situation, laminar flow, you will have to give something order of something 100 diameter of the tube, which is much higher, which you cannot afford to give in case of Bunsen burner or in case of LPG stove burner. But however, you will give sufficient so that profile, some certain profile will be developed. How to maintain a stationary flame? Basically, you will have to keep this maintain the fuel flow rate constant. The flame will be stationary. Of course, in this case, even though the fuel you will be changing little bit, but it won't change. But once you go beyond certain fuel flow rate, or in other words the velocity, right, the flame will blow out. And in case of the fuel flow is less rate, then what will happen? The flame will get into the burner, and then it is known as flashback. We will be discussing about that, about the blowout and then flashback little later on. So, with this we will stop over here. In the next lecture we will be discussing about the laminar premixing flame, laminar premixed flame. Thank you very much.